Hello, I'm Fabio Bottalico, PhD student in mechanical engineering, and today I'm presenting a sensor-aided camera calibration method for 3D digital image correlation measurements. The motivation behind my research lies in the need to continuously assess the health of aging structures. We use structural health monitoring techniques, but the traditional approaches have considerable drawbacks. A visual inspection on a structure like a bridge requires sending a crew of people, thus blocking traffic. If we want to use accelerometers or strain gauges, which are contact sensors, we only have data at the sensor's location. So in our lab, we use computer vision techniques, specifically 3D digital image correlation, because of the ability to reconstruct the shape, displacements, and deformations of an object just using two synchronized cameras. On the left, we have the classic tensile test on a dog bone specimen with an overlay showing the deformations computed with 3D-IC, and on the right side, we have the evolution of a hairline crack under a bridging lowell, still computed with 3D-IC, and both show the versatility of the technique. 3D-IC requires the cameras to be calibrated, which means computing the lens distortion and the two cameras' relative position. We typically do it by taking pictures of a calibration object, like a checkerboard or the colored cross you can see on the left. There are, however, two problems. Problem number one is that the size of the calibration object must be equal to the size of the field of view. So, to test something that is 25 centimeters across, we need a 25 centimeters checkerboard, but to test a wind turbine that is 60 meters tall, we now need a 60-meter checkerboard, which is impossible. Problem number two is that since we are computing the camera's position, if one of them moves, we invalidate the entire process, and we must do it again. So we usually lock the cameras to each other, usually using a rigid bar. Both problems greatly limit the use of Stereovision in SHM. So we decided that we can measure the camera's relative position using sensors, specifically 3 inertial measurement units that measure the rotation angles and a laser to measure the distance, all mounted according to the schematic you can see on the right, while on the left you can see the real-life prototype that we built. To test the accuracy of this new method, we set up an experiment with a large field of view. You can see the two cameras on top, and on bottom you can see the view from the cameras. The idea is to track the motion of the target in a 3D space. So we calibrated the cameras using both the proposed sensor-based method and with a checkerboard. We then took pictures of the target moving and processed them with a tracking algorithm. Here you can see the results. On top, we can see what the tracking algorithm sees using the sensor-based calibration. On bottom, what the algorithm sees using the traditional calibration. The color represents out-of-plane motion, so if it becomes blue, it means it's coming towards us. On the right side, you can see that we took the difference between the two results in all three directions, and you can see that the largest difference between the two is 3%, attesting to the accuracy of the sensor-based method. Thank you for your attention.